seem to be back on track. Hi, my name is Glauber. I'm an associate partner at Robert Stern Architects, and I just want to thank you guys for having me here, Susan, Shavita, for the invitation, and this afternoon. So what I'd like to present is a project we did for Yale University in New Haven, Connecticut. This project was in our office from 2008 to 2017, and we were responsible for design, construction for these new colleges here highlighted in the top, in this kind of triangular site. So this project is for Ben Franklin College in the foreground, and then for Pauli Murray College in the background. This accommodated about 900 students, which was a 15% increase for Yale's undergrad enrollment. They became the 13th and 14th residential college at Yale. And they're named after Ben Franklin, whom you probably know, and then also Pauli Murray, who was a civil rights activist, legal theorist, and Episcopal priest, and also a Yale graduate. The project from the outset was primarily about parity with all the rest of the colleges. So we didn't actually, come up with necessarily this style just for the project. The history of Yale with all its colleges is all the students are brought into a college when they're first come to Yale. They're given a college at the outset, and then they stay in that college for 4 years. So it's very important that they have the same experience across the whole collegial lifespan. So with that, let me go to the next slide here. Seems to be stuck. Apologize. Okay, not working. Still not working. It's the wrong. Sorry, I don't know what's going on. It's the wrong. Okay, there we go. All right, now there's something. So let me try and back up here. Well, so I'll just, hopefully this will move along. I don't know why it's doing this. There, is that better? Maybe it'll work. Okay. All right, now we're back on track, I believe. So an important part of the whole process is just understanding the precedents. So the first residential college was designed by James Gamble Rogers for the Memorial Quadrangle with the Harkness Quadrangle. The motivation behind the quadrangle was to provide communal accommodations for upperclassmen who were pushed off campus by a growing enrollment. And they were pushed out to boarding houses, and they had to miss out on a lot of informal social bonding that the president thought was very important, and then they would become the underpinning of the Yale experience. So there was a competition to have this building. There was construction began in 1930 for all the colleges, and then by 1940 they had built 10 of these residential colleges, becoming the backbone of the college system. This is often based off of Oxford and Cambridge's Gothic college system. Then additionally, in 1940, post-World War II, when they hired Eero Saarinen to provide another project here, another college. Our design work was guided by extensive research into Yale's existing architecture. Here we have James Gamble Rogers' proposal. This was his competition entry, showing the massing that he presented, and then one singular image here of the planning, which shows a entryway system which was in place for Yale since the 1700s, which has a stair in the center, rooms on the side with 2 studies, and then bedrooms that come off of each of those with a bathroom in the center. So that has always been the kind of precedent for the college system at Yale. So for us, that was not feasible based on building codes. We had to modify that into this, what we call a fantasy bar, for us to study that kind of idea, but still having 2 means of egress, an elevator and bathrooms and such. So we've shrunk down that and we're able to squeeze in everything, and then also maintain the same footprint and bar width, very similar to what they had in the other buildings, and then also the same floor-to-floor heights as well. We're 9'4" floor-to-floor heights, and then also trying to maintain the same sort of mechanical systems as well. So all naturally ventilated with hallway mechanical systems. So knowing all this, we then also went into looking at developing an inside-out approach. So here we are looking at the massings of the buildings and how the courtyards would be shaped, and the placement of these elements, and then also the bulk and massing. Actually getting all these dorm rooms on the site with proper courtyards was a challenge. And so we also looked back at James Gamble Rogers' ideas too, and there was some very good sustainable ideas and ways in which he massed and bulked the sites, where the masses would be on a north-south axis would be the tallest buildings, and then the ones on the south would be the shorter masses, which allowed as much sunlight into these courtyards spaces as possible. Additionally, we also built an entire model of the college of Yale, so we can get a scenographic understanding of how all the other buildings and colleges on the campus were laid out, and then see that in context with our 13 and 14 colleges as well. We also were then able to sight line where the towers were located by literally using string. So when we were placing the towers, the important part was to locate them so that they were at the end of an axis of a street, or to pull you across long avenues, because there's a large, and you can see in the foreground, a large graveyard that broke up the main campus from where the new colleges were to be placed. So when we started, we weren't sure if the project was going to be Gothic or Georgian. We did know that they wanted a traditional building. Yale was very explicit about that. So we looked at different options, and there's many precedents for both Gothic and Georgian on Yale's campus. And ultimately, it was determined that Gothic was the best for many reasons. One, the local context right around the buildings were mostly Gothic, plus the triangular geometry of the site really lent itself for a Gothic layout and planning. When we started to develop the project, we studied many options of brick and stone, and here looking at Jonathan Edwards as maybe a very close idea, and then also looking at the window-wall ratio, and then analyzing what that was. And the traditional architecture had a benefit in energy savings by just keeping with that language, and we kept our window-to-wall ratio closer to in the 20% range. And that really helped our LEED Gold target, along with other measures. As we went through different phases, we built many models, large-scale models here for viewing. You could actually put your head inside those models to really understand how corners came together. For viewing, rather than just looking at it on the computer, it was very difficult to get an understanding of how these things worked. And it was also an efficient way for us to resolve a lot of architectural issues. Another important part of our process was looking back at what the rest of the campus had. So we created a catalog of all the different types of elements on Yale's campus and about 80-page booklet of each type of element so that we could refer to it during the design process as we flushed out these elements. We also used this all the way through construction for reference as well. Additionally, we did the project in BIM along with Gary Technologies, and this obviously helped us with coordination of all mechanical systems and all the different complex elements. There is not a lot of repetition in the building in certain ways, like the planning of it does not lend itself to even layout of rooms, although some of the elements are repetitious. The tools were very helpful in helping us coordinate the structure, also to retain that very diminutive characteristic of the rest of the campus, and all those other Rogers precedents which I previously mentioned. Additionally, we used Gary's Technologies software to help us where Revit wouldn't fill in the gaps. So we weren't able to model everything with Revit. It couldn't handle the geometries we were talking about that we were really looking for. Window surrounds, towers, profiles, all the precast elements. So we worked with Gary Technologies to help us come up with these things. And our process was really to use from hand sketch profiles that you can see here on the bottom right to bringing it into the GT software and then parametrically apply that to different elements. Here, a passageway arch where we could modify the radius and then update all these elements and then bring that into the Revit model as a generic model, which was a relatively fast way for us to study all of these elements. Additionally, we also used those models to generate the two-dimensional construction documents and also supplemented these with 3D views, which were very helpful in the construction process for the fabricators and contractors. While we were doing that, we also looked at precedents from Rogers' documents and how they've documented their building. That was an interesting foray, and we also took some of those cues into how we documented things as well. Like Rogers, prior to the start of the construction, we oversaw the assembly of a physical mock-up study model. This helped solidify decisions about the construction, as we had 1.5 miles of a brick facade that wrapped the colleges. This 30-foot mock-up effectively demonstrated the technical and aesthetic qualities for the facade for both us, the builders, and the client. This helped us test out assumptions on constructability and cost, and set the quality and standards for subcontractors that they'll later submit bids. It featured brick facade, obviously here, limestone, granite, granite trim, cast stone copings, window surrounds, actually the windows, the slate roof, the gutters, actual slate, and also this a wood door. So this was all supplied by different manufacturers to test out fabrication and also different techniques. We also tested out the air cavity system, the wall assembly, to see if there was any constructability issues, the flashings, things like that. Then the on-site management team from Dimeo included about 40 staff during construction, which for a CM team was very large. And during the intensive periods, I think it's important for us to remember how many workers were on the site. We had 608 construction workers at the peak, and then typical of 432 on a daily basis, or average, I should say. And so now just moving on to some more specifics about the facade design. So brick being probably the most significant cladding material on the building, which we carefully selected over with many, many different mock-ups and many different manufacturers. We selected this brick from Old Virginia brick, And we are placing our order for 1.4 million bricks, and a month before the order was ready to be complete, they went out of business, which, you know, there's always one that goes out of business on your project. Hopefully it's only one. So we had to move very quickly and find another manufacturer. Luckily, there's other manufacturers out there that are eager to help. And we went with a Glengarry brick, which actually came out quite lovely, and we're very happy with that. And fortunately, the construction schedule wasn't impacted in any way. We all were able to make that work. So another important part was just let me go back one just to talk about it. So the building frame itself is a concrete frame with 6-inch CMU. So it's a flat plate, 8-inch concrete frame. And then the 6-inch CMU, we selected to, save cost. And that since the floor-to-floors were so small, we were able to do that. And that also helped us keep our low floor-to-floors and our narrow plates to work and reduce the beam depth over those window heads, which was extremely tight. And then here our typical wall assembly, which is on the CMU, we have a vapor barrier by Henry, and then Prosecco at the window jambs, and then a 3-inch polyiso insulation, which we studied in great detail about what the appropriate thickness would be through cost modeling and life cycle analysis. We have 4 inches, 2 inches, 3.5, all the different materials, and we ultimately landed on the polyiso being the best payback of under 20 years. So, and then additionally, we also looked at the very important flashing detail here with using zinc-coated copper, because we were very concerned about the expression of the flashing joints at the drip edges. And then additionally, we also were able to use 106,000 different custom brick shapes. So here, taking these bricks and creating the arches, and then the window surrounds, and many other unique elements that helped create the character of the building. And then here, just using some cut bricks to create a little Y below a decorative cast stone band. And then additionally, for the windows, another important feature, we had 4,280 different windows, and as a point of perspective, the Empire State Building has 6,000, so it's quite a bit of windows. And so we were looking at Rogers' windows that he used, which are also steel framed. We used a similar steel framed window, but looked at to improve its thermal performance significantly than what Rogers had. The original one was just a steel window with a storm pane and a lead-camed glass, so it didn't perform at all. But what we looked at doing was to do, which you can see on the left, a lead-camed window with historic glass, and then a high-performing IGU behind that, and then that would be a vented lead-camed window. And then these are all operable windows, as I mentioned before. All the student dorms have natural ventilation with passive heating and cooling systems above them. Additionally, another important part was the blocking at the window. Now, when we drew the building, we were just drawing in either metal tubes or wood blocking, just you would typically with an X through it. However, when Dimeo was brought on, we discussed with them and coming up with this to be a prefabricated blocking system, which would then lock into the MO and the window surrounds, so you could have it all perfectly engineered. So it all come from a shop pre-manufactured and labeled for each window that would be scanned with a little ID on it and brought to the right location, and it cut down significantly. I think we only had to remanufacture one of these on the whole job. So much more efficient. And then here you can see some of the windows being installed. We did even have, you can see little squiggly lines there, grapevining, which is a historic idea that came from Rogers. This is how you would repair windows, lead-camed windows, before you could replace the light. So that charm was important to the character of the building, and so we had to actually map out those in the drawings. And the other ones, the colored lights, that are also placed there. At one point, the contractor asked us to draw every one and map them all out. We did all that, and then the window subcontractor came back and said, no, I'll just do them randomly, which is really how they did it originally anyway. So, you know, a wasted 2 weeks of work. But I go on. So roof details. So another important part was the roofing. It's really quite a significant part of the building design. So we have two types of roof. We have a graduated slate roof, which is, it gets thicker at the bottom and thinner as it goes up. So it starts out at somewhere around 1 inch, which is 1,000 pounds a square, which is quite heavy. So it's quite a significant structural detailing. And then we also have a standard slate detail. So here you can see the gutter detail that we came up with, which is all based on flowers and fauna from Connecticut. And then custom downspout covers as well. So all of that slate, which is from sloping roofs of varying heights, is about 165,000 square feet of roofing, approximately 50 truckloads from Vermont Structural up in Vermont. So the other here is just the roof assembly was obviously a insulated SIPS panel sitting on a metal deck with Benz glass on it and a vapor barrier, and then we put on top of that whole SIPS panel a slip sheet up here as well. We didn't use felt, but then 2 layers of plywood for extra anchoring in the slate because of trying to make the slate and all that last as long as possible. So we wanted to anchor it as well as we could. Then additionally, the standard slate roof here, so this is not the graduated slate. Here, this is more typical of the building. The graduated slate's only on the lower portion of the building to save on cost. And then also a vertical wall. This helps to reduce the mass of the building so that it doesn't feel as imposing. We also had to go for NFPA 285 to go and look at this assembly for the slate, to have that tested and get a letter to confirm that would work. Luckily it passed. And then more details here just to look at, how we did the conductor heads, which I mentioned before. We had tried to have them scanned from originals because we did some replication. Some of them we designed ourselves, but some we replicated. So we asked to have them scanned and then a foam form to be created. However, the subcontractor decided it was too hard to do that, and they went back to just taking them off the existing building and then copying them, which took some doing, but they got it to work. Seems to be, oh wait, there we go. Another important part was the dormers. So this one was able to be prefabricated on the ground, brought in on this little rig. So all these were made off-site and then brought in place. We had some, I think it was 60 or so dormers. And so then they would be hoisted into place because we had tower cranes all over the site to pick these up, which vastly improved construction speed, as well as also prefabricating deck planks too. So the roof decks were brought in large segments and then lifted into place. Another important part was chimney fabrication, which I'm sure all of you deal with all the time. So we had some 50 different chimneys on the project, and for this project that's actually used for intake and exhaust. There are 4 chimneys that are actually actual chimneys, but for these we did them all as prefabricated elements. We worked heavily with BPDL on the project, and this is a 4-sided form that has 2 different colored pores in it. So the limestone piece is 1 pore, and then the brick color is a 2nd pore, and all of that is brick embedded in those precasts. That saved on scaffolding costs, time, and then also not having to have a mason up on the roof. It was actually also lighter in the structure as well, although you do get this weird point where during construction the chimneys would be hanging out on the steel frame and there'd be no brick below it. Another important part was the passageway design. Okay. So the passageway design here, you can see here, James Gamble Rogers also had passageways, but his weren't structural either. He did some other interesting high-tech ways of dealing with that. So ours were fabricated on precast panels and then hung on rods from the slab above and then actually jacked up into place and then grouted into place, and then the wall was built below them to support them. You could see it on the right. Another important part was the tower construction. Due to its size and shape, doing it traditionally was prohibitive. Trying to get the scaffolding up to that level, very difficult. So we went to panelize it with, again, with our good friends from Canada, from BPDL. So it's brick with precast elements in it. This one was 216 different panels. That were fabricated, and then we did all this with Gary Technologies as well, software, and then they were able to actually use that fabrication model for their use. Almost went direct to fabrication, but not quite. So here you can see some of the panels. Here's the tower going up and almost in place, and then other portions are the limestone detailing. So we also have natural stone on the project as well. So here you can see some of these elements. They were all brought into the factory and then flushed out and brought and palletized so they would go to the right spot on the right building at the right time. So this is a major logistical effort for Dimeo to manage. So interestingly, we had two different fabricators on the project. We had Bybee Stone in Indiana limestone fabricators. Bybee using a more traditional method where they'd use planer saws and just plane out profiles the way they've been doing for well over 100 years. That machine is probably over 100 years old. And then we also had with ILC, who did most of their work with 5-axis machines. But both came up with the same results. Okay. So here's, it just stopped on me again. I don't know there we go. So then additionally, we also had cast stone elements. All of those elements were done from our Revit model almost directly, which was very helpful. We did try hard to do everything direct to fabrication. One place where we were able to do it very precisely was the cast stone elements for the windows. And so here's an example of that. And then that also helped us more so in the bay windows. So here you can see some of these. There were 50 of those, and those were all parametrically modeled. So we could change them from 4 bays to 3 bays, 2 windows, different bottoms. And then another important part, which isn't so fast to do, but carved stone ornament. So I'm sure not everyone has done carved stone, so I thought this would be an interesting maybe aside. But the way that the typical carved stone ornament works is that there is a sketch that's maybe produced. So you might find a location on your facade, those little pink triangles or squares, and then come up with a sketch and then hand that off to the stone ornament carver, who would then produce either a clay mock-up, like on the top, or a drawing, and then also the final piece on the bottom. So here is one of our pieces that we designed, here with the DNA strands on the bottom, and then telomeres in the middle. On this is an all limestone piece as well. So here you can see that. And then some other elements as well for ornament, because all the colleges have massive amounts of ornament in them, so we're matching again the precedent from that. So some had 800, some had 300, we're at 430, so we kind of split the difference. And then we also worked with Pat Pinnell, and he came up with a whole commemorative ornament set. So there was a long process with Yale to determine what went where and what it was. And then here's some ideas, and maybe you're lucky enough to get your boss carved in stone. Helps with promotions. There you go. And then one other fun part, too, was the entryway gate fabrication. It was very important is the gates on Yale's campus. Samuel Yellen had designed many of the gates on Yale's campus, and they're really amazing pieces. And we needed to do something similar. So we came up with, for the main gates on the project, there's 9 of them. We came up with our own drawings and some concepts of these, and then worked with a fabricator, Zoltan Kovacs, out of New Jersey, who's a Hungarian-trained blacksmith, and then he provided all the gates and hand-forged all of these elements himself, not prefabricated in any way, no welding, all traditional methods. Quite beautiful and touched every day by the students. And then here you go, the final pieces. And then just a quick tour around the building. So here you can get a sense for the courtyards and all those windows, a lot of brick, the tower, the courtyards, another courtyard here, and then the dining halls, and then this passageway between the buildings, another courtyard view looking back at the head of college. This is the head college house, which is kind of a leader of the college. And then another head of college for Murray. And then the courtyard view of that head of college house. And then since we spent so long on it, we decided we should write a book about it and catalog the whole process. So if you want more than 20 minutes of description, you can go and look at this book. So thank you.
Thank you, Kurt. I will quickly introduce myself since I was confused by going back to in-person events and was late to my own session. I am Gustav Fagerström. I'm with Baltimore Engineering here in New York, principal in the Enclosures Group. You saw my partner Eric Verboon moderating right before the break. And I will, without further ado, welcome Dan Popadynec from Socotec, where he's the principal and director of new construction enclosures.
Thank you, everyone. Good afternoon. My name is Dan Popadynec. Thank you for the introduction. I am a principal at Socotec, and for those who aren't familiar with Socotec, it's a multinational professional services firm based in France, but we are known locally, and we're known locally as Vidars, and previously to that, Israel Berger and Associates. And I head up their new construction enclosure group, so I'm a consultant. The topic of my talk today is fire-rated custom curtain walls, and I'm going to present both the opportunities first and then the challenges of this technology. And since I only have about 20 minutes, I would hope we leave you with just a taste of what each of those are. The commercial drivers behind the use of fire-rated custom curtain walls are the price of land, the scarcity of corner lots in our cities, and the need to provide housing with views, natural light, and air on more of their elevations. These are challenges, especially for mid-block sites on our streets. Let's understand and maybe imagine what this technology can enable. The top left is a photo I took from the street of one of our buildings that we constructed about a decade ago. It's of the back wall, where you can see on the left-hand side the new construction building, on the right-hand side a commercial building. Of note is the gap between these two buildings, and it exists over 15 feet tall from the grade all the way up. I see the architectural and commercial opportunity on these sites in the future with this technology and other technologies like it to expand the footprint of our buildings, shifting closer to the lot lines, and as a result perhaps enhance the layouts of the buildings from a larger footprint, enabling views in a direction that hasn't been enabled before. I've illustrated on the right using Porsche Photoshop skills. I took this photo from my favorite lunch spot, looking up at a building which actually I'm not involved at all in its construction. But on the left-hand side, you see a building in Midtown Manhattan. under construction, where on the street-facing facades is a aluminum and glass window wall system, but on its north facade, which faces Midtown, is a concrete shear wall with cladding. You can see insulation down below in yellow. And above is basically cladding over top of shear wall. I find this very unfortunate because the views to the north are incredible. Chrysler Building, Empire State Building, and in the end, they're not able to capture those views. Reimagining it at a right, you can see, again with my poor Photoshop skills, if we could enable these elevations to be more windows, more glass, more views, more apartments, it will help our future. Oops, there's Jim. Maybe I'm glossy again, that's what happened. There. Okay, thank you. Now, this may be the most boring slide in my entire presentation, so I'll go through it quickly. One of the enablers of custom fire-rated curtain walls is the building code itself. In the top left, we've always known that our building code has allowed has prescribed the fire rating of exterior walls based on a fire separation distance, which is the distance between a building and its neighbor, the type of construction, the type of occupancy. For commercial, residential, and institutional, it could be ranged from 0 hours, no rating, to 1 hour typically. The code distinguishes provisions for exterior walls versus openings and windows. And the New York City Building Department in 2015 issued a memo which quite famously had a lot of interesting graphics there on the bottom right, indicating where you could put windows. But what I found in this memo, which is really important for custom fire-rated curtain walls, is what I highlight here. That it basically said for the first time that glazed exterior walls that pass the test for E119 for fire resistance rating are permitted as of right to an unlimited extent. I want to highlight 3 technologies that together with everything we spoke about enable the implementation of custom fire-rated curtain walls that have been done now on several projects my office has worked on. The first of the technologies is fire-rated glazing. These break down into 2 camps, the fire-rated laminates and fire-rated gel-filled cavities. Both work in a similar fashion. The glass vessel that holds either the gel or the laminate are not truly active fire-absorbing materials. They are there. They're somewhat sacrificial during a fire event. This technology exists and has existed, and its track record is through fire-rated windows. Their adaptation to custom curtain walls, where some of the learning curve and investments have been made and some will continue to be made. This includes producing these type of glass at larger and larger sizes, which are more typical in curtain wall construction, and enabling them to be implemented into unitized construction. My firm has seen and sourced these products domestically from the West Coast, from Asia, and from Europe. These manufacturers are not one-stop shops for all your glass needs, like certain large glass fabricators, which some of them are here today. And that has created one of the challenges here, is that we are pairing fire-rated glass manufacturers with traditional glass manufacturers to produce the next technology, fire-rated insulated glass units. One of the most common intents of architects and owners is for uniformity across their facades, so that when an occupant in a residence doesn't necessarily know or can see a difference between what is a fire-rated wall and what is an unrated wall facing a street or a court. That's easily said, easily asked for. It's actually relatively easy for a facade consultant like me to specify that all the glass should be the same, but just add the fire rating, but much more challenging to accomplish. I'm showing here 2 insulated glass units. The one on top is a very typical IGU on one of the projects we did, and on the bottom is its associated fire-rated insulated glass unit. And right off the bat, even if there's just a section, you'll notice that the thickness of the insulated glass units is remarkably thicker for the fire-rated glass, between 32 millimeter and 52 millimeter, and it contains much more complex assembly of glasses, laminates, infills, and the like. The thicknesses, the low-E coating, which is part of an insulated glass unit for thermal performance, is maintained on the inward surface of the outboard light. On the traditional IGU, it's placed on the number 2 surface. On the fire-rated, because of the manufacturer and the requirement to provide UV protection for the fire-rated gel, we have to put it on the number 4 surface and introduce a laminate on the outboard light. Because we're moving from 2 plies of glass to 5 plies of glass, I want to caution one thing, that it is very necessary to understand that with that much glass, looking through that much glass, you have to make sure that we're rendering the color the same. In order to achieve that, we definitely specified and used low iron glass. There is more than 25% more glass in weight on the fire-rated glass than on the non-rated glass. So this complexity, the weight, is challenging the industry to be able to source these materials for the fire-rated curtain wall construction field. On the matter of aesthetics, I want to focus on one key challenge with glass in general, and multiply fire-rated glass in particular, and that's flatness and distortion. With a makeup as complex and as thick as these fire-rated glass, it's even more imperative to establish realistic expectations for flatness, lack of waviness, and overall uniformity of glass. I'm speaking of distortion in transmission, looking through the glass, not just in reflection, looking at the building and how it reflects the neighborhood. To control and evaluate glass quality, I have to start with the specification. I'm going to say that samples that we ask for, 12 by 12, 2 foot by 2 foot, are useful for some things, but they're not very useful for judging flatness and distortion. It is critical to see these full assembly glass at project size, and that these are the full rated panels, not just the individual pieces of glass coming off the heat treatment line, but the fully assembled fire-rated panels against either some kind of background where we can judge whether it's rendering the transmitted image true, like a zebra board, or a brick wall, which is very likely what you'll be looking at through these fire-rated curtain walls. The one thing we want to avoid is a moment of surprise once it's installed in the building and looking through the glass that we see distortion that wasn't expected. Visual mock-ups. A key step in any project, and especially one with fire-rated glass, is visual mock-ups to achieve the designer's intent to have seamless construction between what's rated and what's not rated. In this case, the mock-up did include elevations of both fire-rated and non-fire-rated components, and glass was seen side by side. You could see it in the middle photo and the right-hand side photo, and good luck to you trying to identify which one of these is a fire-rated versus non-fire-rated glass. The color consistency from inside was very well accomplished, despite the thicker and more pliable glass. Moving away from glazing, the last key technology enabling custom fire-rated curtain walls is development of unitized steel frame curtain walls. For comparative purposes, again, I'm going to first show you a plan section above of the exterior glass corner of a non-fire-rated curtain wall and compare it against, at the same scale, a fire-rated curtain wall below. The top is all pretty standard, 3/8 glass over 3/8 glass, aluminum framing, structural glazing, etc. What below comes to mind is a matching steel profile. The sight lines neatly match. It's still a relatively 6-inch deep system with a 4.5-inch sight line, and the exterior expression of the 2-inch trim achieved relatively closely with the trim on the unit below. In essence, the aluminum is an interior and exterior veneer over a welded fire-rated and inch-and-mesh material system that also works for air, water, thermal, and other performance requirements. I want to highlight that the backbone of these systems tends to be steel. The steel can be exposed to moisture, so it's critical, as shown here, that it be galvanized. One feature in most curtain walls is the classic glass-to-glass butt joint, without exterior trim or other fittings holding the glass in place. In non-rated curtain walls, this is done typically, as shown here in the bottom right, with just structural glazing and some wet sealant or gasketing. In fire-rated curtain walls, this can be accomplished and has been accomplished using toggle glazing technology, which has existed for some time. What I'm speaking about is that the glass is actually held to its steel frame with a patch plate. That, let me see if I can come over here. I can see it's green on white. That plate there, which embeds itself in notches in the insulated glass unit and is bolted back to the steel structure. The notch occurs in the secondary seal of the insulated glass unit. The outboard glass which has the low-E coating, is structurally sealed to the inboard glass with traditional secondary structural sealant. The outer glass is sacrificial in the case of a fire test. Okay. Here are some clear photos from the shop showing this toggle glazing. One minor concession that has to be recognized is sometimes these joints between glass have to grow. In our case here, they grew from what was traditionally a 3/4 inch joint between glass panels to just about 1.5 inches. But on the whole, this was 15 stories in the air, and it was a concession reasonably made because the building rendered itself very well. Now, without getting too much detail, because I am actually not a fire engineer, I would like to talk to you a little about the fire tests in order to achieve a rating of the hour. The most basic information is the following. Each custom curtain wall is used to having a mock-up, and we do this for performance like air, water, and structural, but now we need to add to it a fire test. The industry standard is ASTM E119, and it's adopted here in North America. It's a different standard in Europe. Keep in mind that laboratories ready and willing to handle the size of mock-ups for custom curtain walls are few. Maybe they'll grow, but in general, we need to use within the laboratory's limitations. And so we created specimens which have multiple units. In this case, 2 units wide, 1.5 units tall. 1.5 meaning the bottom one is a non-project size unit. Why are there 2 specimens shown? And this is a really critical part. The code in E119 indicates that fire rating is directional. It matters on which side of the wall is the fire. Per code, shown at the left here, when fire separation, the distance between your building and adjacent properties, is less than 10 feet, the wall must be rated from fire from both sides. It's as if a fire is occurring on the neighbor's property, rooftop, setback, terrace, or building, or from your own building. When that fire separation distance exceeds 10 feet, the wall has to be rated only from the inside, from your own property. What I want to indicate here to you, mostly in the middle side, in this middle part of this graph, is what's called a fire temperature curve of the E119 test. I've indicated here on this graph, time on the horizontal, temperature on the vertical, that the 1 hour test, which is the first dashed red line, is quite beyond the capacity of aluminum to after its melting point and after it becomes molten. Now this one, I'm going to try to do this properly. Let's see if I can make this work. This is a video. Oh. I decided to put 4 screens at once, just in the essence of time. This is a fire-rated test of a custom curtain wall. You can see on the top left, which is the active video right now, 12 temperature sensors on the glass, each of them trying to measure whether the surface not exposed to fire keeps below 250 degrees Fahrenheit. Inside that chamber is a 1700 Fahrenheit degree fire. And what you just saw there was actually the breaking of the interior surface of the glass, and now you see the activation of fire-rated glazing there as it turns from transparent to translucent. I'm going to pause it. Oh. On the top right now, the activated photo, let me just put this pause for a second. Oh, I'm having this. Is about 59 minutes into the same test. What you're seeing here is an unsuccessful test as the fire is breaching through the glazing material. And in a few seconds, you'll see what happens. I want to highlight that this is an extremely violent test, somewhat unpredictable, and when it doesn't go right, it incurs quite a time penalty. The takeaway, it's very challenging to pass these tests at 60 minutes. It's a race against the clock. We can learn and improve our systems, build new curtain wall systems, ship them to the lab and repeat the tests, but all of that takes time. You can see how the fire is breaking through. Give it a second. And with that, because it didn't reach the 60-minute clock, the test failed. The specimen did not work. I want to repeat this if I can try to figure this out. As I mentioned, we tested both sides. So this is the test. You can see the vertical mullions when the fire is originating from the inside of the building that we're building. The one on the bottom left is actually a fire originating from the neighboring building. It passed, and this is what it looks like after the 60-minute test. They removed the specimen, and this curtain wall originally looked like this with the vertical fins. So you can take a look at what it looked. Oh, I'm not getting a little jammed. What's left of that curtain wall having undergone a 1-hour test. All the aluminum is gone and melted and sitting in a molten mess. It's moved to adjacent chamber, where in the E119 test, there is an additional test called the fire hose stream test. Let me see if I can stop that one. This is the hose stream test. At the bottom right is the final test. It is not to replicate what a firefighter would do to try to stop a fire. It's to verify that there is an adequate additional performance after it. We don't want the water and the materials penetrating through the wall. So there has to be a certain amount of redundant performance. The materials can fall off, but there can't be a penetration. Oops, sorry. Let's see if I can do this right. I'm going to go quickly through the last steps, given that we're short on time. But after we did that fire rated test, including the failure and retesting, we did a complete performance mock-up for air, water, structural. It was key to do this after the fire test because of the changes we had to make. This mock-up, which you can see here on the right-hand side, had both fire-rated and non-fire rated components. Why? Because they had to interlock. Well, that's my own clock. By the way, you're not the only one testing me. In the end, I'll quickly go through the last 3 slides. Fire-rated curtain walls, especially these, require not traditional anchors, which are shown there in aluminum construction. These are steel-based anchors. One key thing, steel and welding of steel on site, glass does not like it. Weld splatter damages glass more often than you think. This is an entire bolted assembly, no welding on site with steel components. This is the installation photos. My last tidbit, learned through hard knocks. Depending on the fire-rated glazing you use, it could be very temperature sensitive in cold environments. In a sense, the glass can freeze during shipping, installation, or construction, depending on the technology you use. What's shown here is we actually had to heat up the curtain wall units in transport and on the floor, and after we constructed the floor, we had to provide temporary heat for the entire floor until the building mechanicals were engaged. Otherwise, that type of freezing is irreversible. When it thaws, it doesn't go back to a fully transparent state and would require the replacement of glass. Because of the weight of glass, look at the size of the manipulator to hold this glass. This is something best avoided. I could speak more on this topic, but I think my time is up.
Next up we have Stanley Yee, who is with Dow and a facade design and construction specialist, coming right up.
Thank you. How am I projecting at the back over there? Thanks very much. I'm going to do some furniture moving because I'm sure to trip over this in a minute.
As Gustav said, my name is Stanley. I'm with Dow, mainly hailing from the silicon side. I'm a facade design and construction specialist, hailing from the R&D division. I'd like to thank you and take this opportunity to welcome everybody back in person. I can't tell you how happy I am. Some of my friends out there in the hall, whom I haven't seen in at least 2 years, found out the really direct way how happy I was to see them. I'm here to share with you some real solutions for some real performance environmental challenges in the building industry. Primarily, we've talked about it this morning, and it's probably going on in tracks A and B. I just noticed how we've kind of separated all each other, so hopefully I can take this opportunity to bring elements of those tracks into this room for you while we're talking about the materiality and design and the use of materials in the built environment. But it's also, in addition to talking about reducing carbon, it's about ensuring safety while exerting an expansion and pushing the limits of what we frame in our minds in terms of allowable strength, and extending the life cycle and performance of buildings. And all these solutions are made possible through advances in material science. So we'll talk about sustainability first, because that was the first one, right? How many were you at the keynote first thing this morning where Attila said, we need to do better, right? And I think it comes from, we take it to heart. I have a personal vested, connection to that statement. We need to do better, and I think we can do better, and I think that's built into the aspirations and ambitions that the company I worked for, was the reason why I'm there. Is we aspire to be the most innovative, customer-centric, inclusive, and sustainable material science company that services everybody in this room and the built environment that we enjoy outside. And that's really evident in our 75-year history in the built environment. It's about advancing building science through our broad chemistry set, depth of offerings, and continual strive for innovation. And specifically in the business that I'm aligned to, is that we're really focused on the facade side. So this is World of Façades, so let's not forget that is our focus, but there's a broader context of where we engage, and that's in the walls and facades, windows, doors, and building elements. Pretty much everything you see on your upper left. Sorry, I had a moment there. So it's on your upper left. So, and that's where we're going to focus a lot of our discussion today, in focusing on that notable focus on the facade components, and how our success is culminated by looking inward first. And I think that goes back to what we talked about this morning. Do better. How can we do better? We look at our individual units and how we can innovate cross business, and then carry that through and bring that to and collaborate with the industry, what we call the value chain or the stakeholders. I'm going to simply say, just about everybody in this room, track B, and track A, everybody out in the lobby. It's about how we collaborate to get there. And it's through that collaboration that we're able to establish a firm history. It's really evident in how we innovated 50 years ago for the first structurally glazed application in a facade. Still in service today, and will continue to be for the foreseeable future as long as the owner wants to maintain the building, but it still performs. And that is the culmination of the collaboration and the innovation that has come together that allows us to, design aggressively and design aesthetically and design with performance in mind. And with that in mind, it's not only just, being a reliable source of silicone sealants and coatings, or providing and ensuring that we are always there for the industry by providing knowledgeable service and support, and really backing the products and solutions up with meaningful performance and warranty. But today, it's also about demonstrating leadership in sustainability. And how we do that, or how we have been doing that, is really taking a hard, close look at even our own operations. I think before we know, and we have proven data that shows long-term durability and performance. This is not just us throwing it in the wind. It's connected to a real project, and it's connected to a real kilograms of product. And it can potentially contribute towards acquiring additional green building certification points, as you know, at least through LEED and through GREEN. There are programs and mechanisms for that. And how we can declare and how we can share that there's a carbon neutrality to it, it connects the story that I just shared of 50 years of performance and durability, combined with the steps that we've taken to reduce our own carbon footprint at the manufacturing stage. And that's the introduction of the concept of this carbon equation and carbon balance. And with that benefit over the lifetime of this, take for instance, sealed windows or insulating windows, there has been studies that actually showed that the carbon equation is in our favor when we use silicone technologies, because it's literally 20 times benefit. Could be more, actually. Some documents say 27.7 to be exact, but I'm going to use engineering numbers, anywhere between 20 and 27 times benefit over the embodied carbon of the manufacturing process. So, and all that's connected and enhanced by and built on the foundation of our structural glazing advantages that we have out there. Again, talking about 50 years performance, reliability, track record, and about enabling design advanced and eloquent and aesthetically pleasing design initiatives that we talked about a lot today, including carbon. Building on the structure of silicon, so it's moving away from sustainability. We kind of pivot over into advanced engineering, because it's you can already tell we're not at all about just sitting still and resting on our laurels with our solutions. We want to continue to be able to provide advanced engineering, advanced solutions, and particularly through advanced engineering, start implementing smart, strong silence for taller buildings, enabling larger lights, reducing the use of metal framing. There's lots of interpretations of what that is, but there's an opportunity to reduce that, and be able to use that technology to kind of give us more than just your standard rectilinear shapes. And we saw some examples in this morning's presentations, which were very intriguing. So it's about harnessing silicone strength, and it's all high performance by design. The fundamental notion that it's a continuous, flexible rubber anchor, a unique combination of strength, flexibility, weather, and UV resistance, all needed for this application. I mean, that's the fundamental building block moving forward. Then taking that fundamental building block and focusing on material behavior. Developed internal expertise in material science, advanced use of and heavy use of finite element analysis to gain a fundamental understanding of our own sealants in all of these applications. Extensive research and testing, which is key, where we were able to collect all that data, and formulates the backbone of a program that allows us to share that there is flexibility to use higher allowable stresses in structural glazing applications when using conventional designs. So we're familiar with how we deploy it. We know what the allowable strength is in the past and historically how it was developed. And because of the data that we've acquired, we can move forward with it. And it's because of this advanced engineering that was key, where we were able to study the behaviors and the influence of geometry. And it's all, so this program is all culminated into a data-driven and science-based approach, which gives rise to the benefit of what? No special sealants required. It's not a special moniker anymore. It's about harnessing and leveraging the proven and high-performance characteristics of the branded Dalsil structural silicones that you know today. And the main advantage of that, particularly for shop applications, is sometimes you need that high design for very specific locations, but not necessarily for the rest of the job. It reduces the necessity to switch out materials midstream, which is often more trouble than it's worth, or more trouble than many of our customers have shared that is desirable. So we're able to kind of harness that capability. The next level, but it's not just about silicone. We're a broad-based and expansive material science entity where we have a broad technology that we play with. And so a lot of times, just really quickly, we use the term fit for use. You know, what's right for the application. Sometimes it's not a one-size-fit-all. And just really, without getting into, because I'm running out of time here, without getting into a lot of chemistry, which is, quite frankly, as after lunch, probably everybody's not into that. So we're going to go stick into the broad-based on the left side of your screen. I finally didn't have a moment. So over on your left side of the screen, we have just a basic spider chart about the technologies that are out there. Organic, inorganic, and things that are a combination of the two. And when you look at the dark blue line, obviously there's a lot of great attributes that come with silicone, strong UV resistance, lifetime, the product or application lifetime, weather resistance, typically non-bubbling, low temperature gunability. These are really characteristics that are great, that are good and ideal for glass and glazing applications. But it's not very paintable, and depending on which products and applications, there are concerns and considerations that need to be taken into account for stain resistance and dirt pickup. On the organic side, it's almost flip-flop. You can kind of see that light blue kind of shift into all the other areas that silicone doesn't reside. Hybrids kind of sit in that comfortable middle space. Not particularly strong in any one of those corners or attributes, but helps bridge the gap between organics and inorganics. And that has culminated into our introduction of a new hybrid solution to fill those precise gaps. So this is now currently available. It's called it's a contractor's paintable sealant. Really harnessed in some applications, there is a desire for paintability of the sealant. It might not necessarily be day one. It could be day 1 year. It could be day plus 5. But nonetheless, there's a desire to have that flexibility for it. So this product is specifically, it's a sill-terminated polyether hybrid technology, low VOCs, low odor, fast skinning, non-staining, non-corrosive, all these things equal makes it better for paintability. Typical application would be, again, this is not a structural component, it's really mainly weather sealing and weatherproofing, great for expansion joints and secondary seals. Particularly when you have a robust silicone solution for the primary, this is a great secondary to be able to, again, provide the customer base or the project with the paintability characteristics, of which anywhere between plus minus 50% movement from your original joint width, and generally primerless adhesion to most typical substrates that would be involved. And of course, like with everything else, primer options are available. Surface temperature being a primarily organic backbone with silicone enhancements, still in that negative 75 to 300 range, with an application temperature of about 40 to 100 degrees Fahrenheit. Not today, but if we were to come back in January and February, on occasion, if it's still minus 20, as long as it's frost-free, still be able to embark on it. Staying on our journey with organic solutions, because again, it's about fit for purpose. Soon to be launched here in North America is enhancing vision and safety. And we talk, and particularly as it relates to glass balustrades. The separation between where we are and where we want to be is breaking down significantly. We really want that high degree of transparency. We really want to break down that physical barrier that exists between us. And glass is one of those solutions, but the glass solution is also as good as what it's anchored to or what it's anchoring. There's various different methodologies how to accomplish this. They all come back with some of these great images of basically breaking that barrier, and it culminates into the 375 solution, which is a two-part solution. It's basically a polyol and a hardener. Because it's 100% polyurethane, it does have its limitations for UV exposure, which calls for a need for a pure silicone top bead or cap bead, and there are options to implement a release agent to facilitate glass replacement. So this really kind of wraps up this whole notion of starting with looking inward, focusing on the environment, reducing our own carbon footprint, leveraging our experience and strength and knowledge and data that we've acquired on structural glazing, and really looking at the different technologies that are available to us, whether they be pure organic, pure inorganic, or somewhere in between through the hybrids. For that, thank you very much. Enjoy the rest of the conference, and I'll be out at the table at the back for about another hour or around. Thank you very much.
So, oh yeah, those chords are deadly. Yeah. Proving the point. Okay, so thanks again, Stanley, for that. Next up is Steve Mort from Tremco. He's a key account executive and will talk to us about a topic that was covered in part this morning as well, which is the local law 97 retrofit, New York financing and the new building envelope. Appreciate it.
Thanks, sir. All right. Microphone on? Perfect. All right, so hopefully everyone's having a fantastic conference. Seeing some of those projects this morning, I really hope I get to work on one of those, because those are like retirement pipe dreams. Seeing the amount of money that some of those facades are being allocated to, it's one of those things that you get to, one of those projects in your lifetime if you're lucky, and then you go play golf or fish or whatever you want to do. Most of our business, most of what keeps the lights on, most of what you probably will be working on over the next 5 to 10 to 20 years is going to be on things like Retrofit New York in response to Local Law 97. So when I was putting this presentation together, I started thinking about, what could I convey to you? And I started thinking about the fact that I'm currently working on 4 projects that are whole building retrofits, deep energy retrofits. And so I started thinking about is, what were kind of the themes or the lessons learned that are happening in real time with each one of these projects that I can kind of share with you to kind of expedite your journey into these whole building retrofits. And some of the themes that I'm seeing on these projects as we're doing these in real times is money, technology, and just the overall design process, and really how those 3 elements are transforming how we design and work on buildings in this space, in this retrofit space. So the first up is the money piece. So regardless of your stance on climate change or carbon sequestering or anything like that, when it comes down to it, it's a financially viable solution. Anything historically that benefits humanity, improves quality of life, improves occupant comfort, industry tends to invest in, whether it's private investors, whether it's the federal government, whether it's state entities. There's always money to be made when you're doing something to improve people's quality of life. So if you aren't paying attention to the news at the moment, this week the infrastructure bill was signed by President Biden, and as of 3 hours ago, the Build Back Better Act is currently on the House floor being debated. Depending on which side of the fence you fall on, that might be a good thing, might be a bad thing. But this is the money that's on the table that will be applied to whole building retrofits depending on what you're going to try to leverage on your project. So all these piles of cash are going to be sitting there, so as you're working with your owners, as you're working with developers, you might be able to dip into these to help justify some of the costs or some of the intent designs of the project. At the state level, and this is an entity I've been working with for the better part of 2 years now, NYSERDA and the Retrofit New York program. When I sat down with their team 2 years ago, we started talking about what would a whole building retrofit solution look like? What does panels look like? What does the roofing system look like? Mechanicals. And finally we got down to the brass tacks of it. I'm like, I can design anything that you want. Who's paying for it? And really that was the question that no one could answer, and so they're slowly working on that. This week, the second round of GAP funding was released for deep energy retrofit pilot projects. So if you have a project, if you have an owner that wants to take advantage of this, that is currently open.
So I suggest submitting an application for that funding. So what we're seeing on these projects, whether it's California, Massachusetts, New York, Toronto, is the capital stack and what money is available, what that money can or cannot be used for is really critical. So there might be a slew of grants that they're applying for, as the roundtable talked about. Maybe you're getting some kickbacks or incentives from utility vendors. There's the CPACE financing, which was made possible, part of the Climate Mobilization Act. So you go to NYSE, you can get certain loans for certain energy service agreements or equipment upgrades. And then there's the penalty piece. And that is a financial line item that owners are either going to have to carry or they're going to have to design around and adjust to. And while that seems really scary, it's the dollar amount that's scaring people. The principle of it is no different than Local Law 11, where you see all the sidewalk sheds up because, they did an inspection, they found out it was going to be expensive to fix the building, and the alternative is put a sidewalk shed up and just pay the rental fee for the next 20, 30 years. So same concept. So on a real project, this might be what your capital stack ends up looking like. You might have a slew of grants, you might have some energy financing, and then there's also the offset of cost avoidance. So that might be what your project is left to work with. You look at a building, you evaluate it, they do a financial analysis, and they say, hey, you have $13.5 million to work with. However, each one of these line items has triggers, has performance requirements, has things that you need to check up on to make sure that you can actually leverage that funding and that you don't fall into default and have to pay that back. Some of the things that I'm currently working on with some of the lending institutions, and they're trying to figure out how to financially leverage it. It's something that they haven't had to do before. So historically, when we started this journey with NYSERDA, they really wanted to try and pay for these building envelopes just on the energy savings. And that's not realistic at all. That comes down to $10, $12 a square foot on a facade in Midtown Manhattan. You are not going to do much retrofitting on a Midtown, mid-story high-rise in Midtown for 12, 14 bucks a foot. So trying to figure out how we can capitalize financially on these other costs. Maybe it's improving tenant retention, lowering some of the marketing costs necessary, lowering their insurance premiums by providing passive flood barriers to buildings that don't have flood barriers today. All those sort of things. Deferred maintenance, depending on the entity. So if you're New York City Housing Authority, the State University of New York, you have billions of dollars of deferred maintenance. You can now start addressing those line items as part of the whole building retrofit, which helps pay for the project. So my biggest takeaway for the money side of things is understand what the capital stack looks like, understand what the money's being awarded for, what the strings are attached to it. So if you have an energy rebate for doing air source heat pumps and you decide not to do heat pumps, that money disappears. You can't use it for new tapware or new doors or anything else. The other thing that was probably a little bit unrealistic at the start of this process was some of the technology piece of it. This is kind of the customer journey that we're seeing with these projects is a building gets identified, it goes through a physical needs assessment. So they tear the building apart, they is there asbestos in it, is there lead, how old's the mechanical system, how well's the building envelope maintained, what's the performance of that building envelope, is it an R1? Is it single glazing? All those sort of, what type of roof condition, what's the roof in as far as condition-wise? And then it goes through just a real high-level project scope, that financial analysis that I just talked about to figure out what they can and cannot pay for in the project, and then it goes through more of a design-build type process. But when we started talking with these developers, when we started talking about with NYSERDA, one of the things that they kind of maybe didn't understand too well was the digital capture process. They really want to make that as efficient as possible. So the intent is you go out to a project, you digitally scan it using LiDAR, you drop it into, or creates a point cloud that you dump into a Revit model, you do your design work, that goes straight into fabrication and panels go up on the side of the building. sounds really easy in process. Gustav could probably tell you that's a lot more complex than, I made it out to be. And we're finding out in real time that if you don't capture the information the right way, or you don't have the right partners on the design side of things, this whole process just really falls apart pretty quickly. So what we're finding out with a lot of these projects, where before they engaged us, they had laser scanning done of the project, they had Revit models built, is they didn't have the discussion on the level of development that they needed or the level of accuracy. So the digital models are pretty much useless as far as actually creating and doing fabrication at this point. So making sure that conversation is being had, making sure you're working with your fabricators, your material manufacturers to find out what tolerances they need to make unitized curtain wall systems or opaque panels or whatever they might be making. Having that clearly defined before you do your laser scanning and BIM modeling is critical. Other things is site conditions. So when we started talking with NYSERDA initially, they just assumed every building in New York City could be laser scanned from the ground. What you quickly realize is if you're in a really tight alleyway, or you have air conditioner units, or fire accesses, or this is right outside my hotel yesterday, all this nice sidewalk canopy and outdoor seating and all this stuff, ground LiDAR scanning just doesn't work. You miss too much data. If I'm standing right here and I shoot a laser to start getting data points, I'm missing the entire second story of the structure. We're also finding that time of the year that they do the scans is also critical. Project in Boston, they did all the LiDAR scanning in the middle of the summer, so it picked up all of this foliage and didn't actually scan the building. So it was a waste. Again, alleyways, trying to figure out, can you get onto an adjacent rooftop, that sort of thing, is really critical as far as digitally capturing the building envelope. So there's other ways to do it. Europe, they're actually cantilevering out some of the LiDARs outside of the window units. Probably not in New York City, but in upstate, they're actually hooking the LiDAR systems to drones to do some of the scanning. That's helping. There's trade-offs, though, because you lose some accuracy when you do it off of a drone versus if you're doing standard tripod. So, again, capturing that data, trying to figure out, is it good data? How good is that data? What can you leverage it for? What can you use it for? Those are all critical things to understand, because it's really unfortunate and disturbing, disappointing, to the owner when you have a really pretty Revit model that they've looked at and they like, and when you go to fabrication, it's, well, the tolerances are plus or minus 2 inches. That's not good enough for fabrication, so someone needs to go out and field measure the entire building again. Those are tough conversations to have. If you do all the scanning right, you have that conversation up front. There's really neat plugins now that you can go for where the system will automatically generate all your shop details, and there's actually plugins that will now optimize your freight. Again, reducing that carbon as far as transferring from panel manufacturers, unitized curtain wall manufacturers to project sites. And then the last thing that kind of we wanted to share as far as lessons learned was the overall process. So again, because this capital stack is so critical to understand as far as what you can and cannot spend money on, and this process is changing. It's not that design, bid, build model. It really has to go to a design, build solution, because there's so much time invested on the front end. To give you an idea of that, this is a project I'm currently working on in Boston, built in the 1960s, R1 wall, single glazed. The specification writer that was speaking earlier would have been very disappointed, because this was the spec. That was it. When we started talking to him in schematic design, we're like, okay, what's the intent of the building? That was the email that we got, and actually it wasn't even the VFDs at that point. They were going to use something else for the mechanical systems, but the big drivers were R30 walls and 0 tenant displacement. This is a fully occupied building, 100% occupancy, and the big mandate is we could not displace a single resident during construction. So this project went into schematic design in October of 2020. We hope to start CDs December 10th. So to give you an idea of the length of the design process. So when you start thinking about January 1, 2024, if I was a building owner, I'd be getting very nervous that if they don't start soon, they will be paying for penalties. What was really neat about this project, the developer was super transparent. She kind of set the stage for everybody, from the designer, the fabricator, the installers, the general contractor, that we will all be incredibly transparent, truthful, and really work collaboratively. So very early in schematic design, they brought us on board. They said, you will be our facade partner, and let's figure out what the right solution is. There really wasn't any talk about money at that point. It was figure out what the right solution is, then we'll figure out how the money works. So part of that integrated design process, when we started looking at some of the mechanicals, even though we're a facade company and we do absolutely nothing with mechanicals, they started thinking about, what was the best way to install this new mechanical system, this new MEP system, without displacing any of the tenants, and the easiest way to do it was to run it on the outside of the existing structure. So after 5 or 6 different iterations where we had 3 siloed trunks, or 3 drops and then trunks shooting across, finally we ended up with these vertical drops at every single floor line because of fire issues and fire separation. So that was the mechanical system they came up with, the designer, the MEP consultant, and they came to us and said, okay, could you design a facade system that can accommodate that? And we didn't have anything off the shelf that worked, so we designed something completely new. So this is the new attachment system. It is a kind of a H-bracket clip and rail system, and then a completely new panel system that is internally framed with non-conductive material, which I can't tell you what it is because the patent's pending. But it really is going to allow this project to take a prefabricated panel with a window-in unit, bring it out to site, and clip it directly on the outside of the building, covering up all of the mechanical systems. So that's what the building originally looks like, and in April, May-ish, that's kind of what the building's going to look like, and the construction cycle time for putting up the entire 26,000 square feet of facade is going to be just under 18 days. So I'm actually short for a change, which is fantastic. I did want to leave you guys with this quote. Whether you believe in the carbon piece or not, it doesn't really matter. Whether you believe in the legislation and funding these things or not, doesn't really matter. Over the next 5 to 10 years in New York City, think about the number of buildings that they were talking about earlier that are going to have to do some type of facade work, some type of retrofit work. If you're a smart business person, you want to get in that because there's going to be a lot of cash and a lot of business. And if you don't want to participate in that, you're going to have a really tough time pulling permits and getting cranes and getting scaffolding because they'll be taken up with all those projects. So if you want your business to survive, you're going to have to play in this space, whether you like to or not. So, fantastic. Thank you very much.
All right, thanks, Steve. We clawed back 3 minutes that way. That's appreciated. You can, of course, do questions and answer afterward with people outside in the circulation area. So now to close up our presentation segment here, we have Brian White from H.B. Fuller Company doing a presentation on Code Space 4SG, the key to energy efficient structural glazing facades. Floor is yours.
Gotcha. Okay, great. Thank you. Thank you. So it's really nice to be here in person. I know I gave my first talk at the Zak World of Façades last year, but I was talking at my computer screen, and it was very boring, and definitely not as exciting as being here in person talking to everybody else. So yeah, as mentioned, my name is Brian White. I work for a company called H.B. Fuller. We're going to talk a little bit about a spacer technology and how it can help enable energy-efficient structural glazing facades. And also, I was hoping to start to draw that link a little bit in between. I think what we've seen, or what I've seen when we attend some of these conferences and some of these talks, is that a lot of architectural design phase, a lot of the specification seems to treat the IG as kind of a black box, like it's an IG and an IG is an IG. But what we want to start reinforcing to the market and start reinforcing to people is that there are options out there in terms of what can I do using the spacer technology to help enable different designs and more exciting designs and that kind of stuff. So, all right, see if we can get this to work. Okay, first, so a little brief snippet about H.B. Fuller. So H.B. Fuller, we've been around for since 1887, so quite a while now. A pretty unique aspect of H.B. Fuller Company is since being incorporated, it's actually never been bought by a larger company. So not too many companies can say that now, being around that long. About 4 years ago, H.B. Fuller acquired a company called Royal Adhesives, and along with that acquisition came a company called Kummerling. We are super excited about that acquisition because it really joined an industry-leading North American insulating glass sealants company with another global and the leading company in the rest of the world, in so much as Kummerling. So right now, that marriage makes us a global market leader of adhesives and sealants in IG applications. We're continuously focused on development, technical service, and improving our game year over year. We also can completely supply IG manufacturers with anything they need in terms of sealant and adhesives and spacer technology now. So we do everything from IG sealants, structural glazing solutions, spacer systems, wet lamination, and we're involved in a lot of that. So you might ask me, and in fact somebody came over a little bit earlier to our booth and asked me, hey, why are you here? And I said, well, that's an interesting question, right? I mean, we're a sealant and spacer supplier, so we're pretty far up the chain in terms of talking to folks that are designing and executing facades. But the reason we're here is because, as I mentioned, we want to try to bridge that gap and create pull in terms of what how we can help enable energy efficient design. And we see these trends in the glass facade market. So energy efficiency obviously is a big deal. One of the things that we see, and I think is becoming very apparent to a lot of people, is that the energy efficiency that we're looking at now is no longer just energy efficiency modeled, simulated, modeled, and what the facade should be executing on day one. Now we're looking at how's that building going to perform 10 years down the road, 20 years down the road, 30 years down the road. It's important that we start thinking in terms of energy efficiency for the long term. Those energy efficiency standards keep tightening. The European Directive 2013 has gone into effect. NFRC we see now is evaluating Energy Star 7.0 and in fact is also looking at Energy Star 8.0. So we're seeing a continuous tightening of energy efficiency demands, and that's not going to end anytime soon. We're also seeing increased demand for innovative shapes. So now, I mean, some of the beautiful buildings we've seen in these other talks today are utilizing shaped IG. We're no longer looking at a rectangle. We like triangles. We like polygons. We like curves. So that we're starting to see a lot more demand for that. In terms of other designs, looking at jumbo units, some of the 10-foot by 20-foot designs that we've seen, or units that we've seen out there, and also increased demand for functional facades. I mean, those that utilize electrochromics or thermochromics, LEDs, things like that. These functional facades are becoming more and more popular as well. So to talk a little bit about why this spacer technology can help improve energy efficiency in the market, we got to take a little step back, and I want to give just a short introduction to insulating glass. I know a lot of you are very familiar with this, so I apologize if it's a little basic, but I want to get everybody on the same page. So IG is basically comprised of four main parts, right? You've got the glass, which provides a vision space. You've got the spacer, which holds those lights apart, creates that insulating cavity, hence insulating glass, and will also contain desiccant because we have to keep that airspace dried out. We can't let moisture in, or we can't let moisture collect in the airspace. We've also got the noble gas, which is typically going to be argon or krypton or some other exotic gas that improves that insulating value of the cavity. And then we've got the sealants, the primary and the secondary sealant, which hold everything together, seal that cavity, keep the moisture out, the gas in, and help absorb and diffuse mechanical stress. So thermoplastic spacer is an effort to simplify the IG design. So you've got the glass panes that we talked about. In a typical IG assembly, you'll have the metal spacer with the desiccant in it. And you can see that, I might as well use the pointer here. So you got your metal spacer and desiccant here. You've got your primary sealant in green along the edge there. And then the secondary sealant, which is going to provide that structural strength for the IG. Thermoplastic spacer and Coty Space IG, as I'll talk about it in a couple slides here, simplifies that design by pulling together the desiccant, the spacer, and the primary sealant. Creates one nice contiguous barrier. 4SG now is a step beyond typical thermoplastic spacers. So some of you that are familiar with IG assembly, glazing, that kind of stuff may have remembered the initial introduction of thermoplastic spacer in the North American market. There were some issues that went along with that, so our colleagues at Cumberland went back, helped develop the product quite a bit more, and came back with a reactive TPS known as CodySpace 4SG. 4SG, in fact, stands for for structural glazing, so so a little bit of trivia for you. The benefits of reactive TPS are that it actually chemically bonds now to the glass and to the silicone. So whereas non-reactive TPS was a normal physical bond like you would see in any kind of hot melt, reactive TPS now actually bonds to all that. And as much as Stanley mentioned earlier today, it's a bit after lunch, so we won't go into chemical structures. It also internally cross-links to build its own strength. That internal cross-linking actually improves the surface temperature of the material, makes it a little more resistant to incompatible glazing materials. So I don't know, some of you that might be familiar with the PIB migration stuff that's happened in the past, this is a little more resistant to that. And it really creates this permanently elastic and fixed and cohesive edge seal. So it bonds with everything. You've got this nice, again, a nice cohesive edge seal that is permanently fixed in place. It's approved in structural glazing applications. It's been in the market since 2009 and has been extensively tested and certified by all the different testing bodies that are out there. So again, I wanted to kind of tie this in because I thought the talks earlier today were really focused on energy efficiency for the long term. So again, now kind of how we approach energy efficiency and how we approach modeling is that we look at something, we say, okay, let's put it in a simulation. We get a U factor, we get an insulation value, and then we say, okay, well that's the energy efficiency of the building. Well, that's the energy efficiency of the building on technically the day it's made, and not subject to any kind of long-term stress or any kind of really anything that stresses that performance. So what we want to do is look at how can we make IG really perform for the long term, because that's the whole point of this, right? It's the whole point of energy efficiency is we want this to perform for a long time. We all know that energy efficient IGs, they reduce carbon emissions, they create a more comfortable interior space for the occupants, they decrease energy costs, all the good stuff that goes along with bringing energy efficiency. The big drivers of that IGU energy efficiency are first and foremost the low E coating really drives a large portion, up to 50 to 60% of the energy efficiency of an IG unit. The gas fill is going to be another 20% or so, depending on what kind of gases are used. And the edge system really delivers another about 5 to 8% of that efficiency. So when we look at the edge system, we say, gee, it really doesn't drive a lot of the energy efficiency of the unit, so why do we care so much about it? Well, the reason we care about it is because it's the ability of that edge system to retain gas and prevent low E damage that drives the long-term efficiency. So again, we look at the gas and the coating making up about 80% of that energy efficiency. Keeping that gas in there, keeping moisture out, and keeping the low E coating protected are really what's going to drive energy efficiency for the long term. So when we look at that and we say, okay, we want to drive that energy efficiency for the long term. Great, Brian, what's the spacer going to do for you there? Well, in order to talk about that, we should talk a little bit about what an IG unit undergoes day after day. So IG units, they endure a lot of different stressors, and I know you're all aware of this, but there's major temperature changes in excess of 100, 120 degrees, depending on what area of the country you're in. Humidity extremes, wind loads, pressure differentials, all these play a big role in creating stress within the IG unit. So when you create that stress, now all of a sudden the sealant, there's stress at high temperatures. What you're going to get are airspace volume changes and glass deflection. So we all know that there's deflection in glass. Moisture vapor is going to start pushing its way into the unit. There's going to be edge seal strain and tension that's going to occur because of that pumping of the IG unit. And then you're also going to get differential thermal expansion of the inboard or the exterior lights just due to those large temperature swings. And in fact, what that's also going to bring about is you're going to have two different size glass panes due to that expansion. So when we talk about all these stresses that the IG unit undergoes, we have to understand the importance of the elasticity when it comes to an IG unit. So as I mentioned, stress results in strain in an IG unit. Rigid spacer systems, unfortunately, they compensate through glass deflection and primary seal deformation. So what happens is when you've got a typical rigid spacer system, you've got your PIB primary seal here, pumping in, pumping out. You can see that you got a very, very little surface area to deal with that daily pumping and the deformation of that seal. What happens is when you have thermoplastic spacer, or better yet, the reactive thermoplastic spacer, it can now elastically deform across this entire bulk of sealant, or a bulk of spacer, and can expand and contract right along with that unit. So that improved stress and strain distribution that comes along with the reactive TPS really minimizes the chance of failure in the field. We can also see a couple other, so again, talking about thermal contraction and expansion. So just visualizing that here, when you've got a rigid spacer system, if that temperature drops, that inner pane is going to stay warm, that outer pane gets cold, all of a sudden the outer pane now shrinks and you're going to get stress on that primary seal. Depending on the dimensions of that primary seal, it could become damaged. Whereas again, with CuddySpace 4SG, that's not an issue. It's a complete non-issue when it comes to thermal contraction. Additionally, when we look at conventional IG and CuddySpace 4SG, we also see a large number of interfaces between glass and sealant, and then sealant and spacer. Each one of those interfaces is a weak spot in the edge seal design. So moisture can make its way in, gas can make its way out. When you work with CuddySpace 4SG, now we've reduced that by half, and we also typically use a much longer path length. So not only are there fewer interfaces, but they're longer, so it's harder to get moisture past or gas past that. We've seen this borne out in industry testing. So what we've got here are, these are units made with CuddySpace 4SG, ran them through cycles of EN 1279, and then checked the gas content and the moisture penetration index as spelled out in the EN 1279 standards. Just for reference, each run is 28 days of cycling, so temperature cycling from -18 to plus 53 C and 95% relative humidity, followed by 7 weeks in the high heat humidity chamber, so at 58 C and 95% relative humidity. What we see here is the initial conditions of the units, so passing dew points, as whether you reference European or American standards. The argon concentration, 93.4%. Now what's really unique about this, we ran it through 5 cycles, so this is simulating decades upon decades of IG performance. What you see is only 12% of the actual desking capacity in the IG has been used up. And we also see an argon retention of, argon reduction to 89%. So really only lost 4% of its argon content over, again, 5 cycles of what's considered, industry standard testing. So for reference, 1 round through this is considered industry, the state of the industry. Another thing that this allows us to do, so with 4SG, is to start enabling better design freedom. So we can see is with 4SG, it's computer, so it's automatically applied, computer controlled. You can do all sorts of different planar shapes. So if you like curved corners, if you like different polygons, if you like whatever this shape is, you can go ahead and any of those can be made. We can also do cold bent IG. We've spent a lot of time studying the effects of 4SG on bending, on cold bending IG, and the way it distributes the forces that are associated with that. You can do bending or also torsion. And in fact, we've got some projects where we've looked at very much improved manufacturing efficiencies when we're able to look at using bent IG rather than flat IG. Also, I mentioned the jumbo units before, but currently you can see some pretty large units that have been made and have been in fact displayed at some of the glass shows around the country. So what I want to do is just show, again, a few examples of projects around the world that have utilized 4SG in their IG construction. So this is the Chadstone Shopping Centre in Melbourne, Australia. It's the largest shopping center in the Southern Hemisphere. The sealant here was actually a silicone. Spacer was CuddySpace 4SG. IG manufacturer Show Glass, and the facade company is Sila. So this was completed in 2017. Here we've got almost 2,200 IG units and about 7,080 square meters of glass roofing. So this is a picture from the inside, and then these are pictures from the outside of that building. So you can see a very dramatic roof, and made possible by cold bending those units. 102 Charlton Street here in New York. So the sealant, or the space here is Cody Space 4SG. IG manufacturer is Oldcastle. We've got the designer is Ismail and developer Lazarian. This was completed here in 2021, and actually my colleague Mike took a picture of this just the other day. So this one, used what we can see is the execution of this facade, and then just how they used Guardian glass to achieve that nice silver aesthetic. So this is the CIBC Square in Toronto, Canada. So we're looking at here is, again, a Cody Space 4SG. So this is actually these two right here. IG manufacturer here is Viracon. The architects were Adamson and Wilkinson. This was completed first. So one tower is completed in 2020. The other is 2023. Looking at 270,000 square meters of glass. It's LEED Platinum certified and meets well building standards. Just a few more of these projects. So we've got the Parnas Tower in Seoul, South Korea, and then the LG Science Park. Together, this is almost 125,000 square meters of insulating glass utilizing Cody Space 4SG. And then also another real interesting project was the TÜV Süd headquarters or the Newton building as it's known in Munich, Germany. So this is, again, a 4SG project utilizing cold bent IGs on the roof of that building. So on the right over here, you can see all those cold bent units. So looking at Cody Space 4SG and how we can help, how we can help bring about this energy efficiency for the long term. What we find, so Cody Space 4SG, it's reactive thermoplastic spacer, so it's important to keep that in mind. That reactivity is really what we see as the next generation in TPS or TPS technology moving forward. You get that improved adhesion of glass, that adhesion of silicone, again, that chemical bonding that occurs with that, the improved chemical resistance that goes along with it, and really setting that edge seal in place. Due to the fact that you can diffuse and mitigate stress, you get really unmatched thermal performance in combination with long-term durability. So again, when I talk about this, it's nice to have a model of an IG unit or of a facade that meets a certain standard. But again, and I think like we talked with the LL97 that we were talking about earlier, we're really starting to look at actual energy usage. So I mean, that's what's important now, not whether you meet a certain criteria. The actual energy usage and the actual performance of buildings is becoming more important as we get further along here. You get excellent gas retention. The product is certified around the world. And it's really used in some of the most demanding facade applications worldwide, as we saw in the examples that we showed. So jumbo units, shapes, bent units, really all of these are possible with 4SG. So with that, I'd like to thank you. And if there are questions, I know my colleague Mike will be at our table and for later on. So if you have questions, feel free to ask him and or contact me via our business card. So thank you.
All right. Thank you, Brian. And as Brian mentioned at the end, I'm sure that Steve, Stanley, Brian, and Dan have themselves or representatives of their companies willing to take questions since we're running a little bit behind here. So now we have reached the closing roundtable of this afternoon session. And it will be moderated by Julie Janiski, who is a partner and sustainability leader at Grapple Engineering. And Julie will do the introduction of her panel members. The topic of the roundtable is the creative approaches of the facade supply chain. So, Julie, the floor is yours when you're ready.
Oh, got it. Cool. Cool. So green to go, red to go back. Okay. Yep. Cool. And you bring up the intro slide, or do I do that on the computer? Okay. How does... Sure. Okay, cool. Great. Welcome. Pick your poison.
Where I want to sit?
Yep.
Are you standing? Are you going to stand or sit?
I'm going to sit here. Thank you. Thanks, Scott. Yeah, absolutely.
What's that? It's old. It's old. I was married in it. Yeah.
Thank you. All right, welcome everyone, and thanks for hanging in there. We are going to have a panel discussion on creative approaches to the facade supply chain, and I have the distinct honor to introduce the folks that I've had the pleasure to speak with a few times leading up to this panel. First, Scott Lee, a partner at Morphosis, project principal and lead of the New York office. Second, Andy Black, a director at New Hudson, specializing in product development and design, supply chain coordination, and many other things. Neil Thelen, a head of project delivery at Neighbor, working on scalable housing systems, among other things. And Lisa Ramig, a director of the San Francisco and LA offices at Eckersley O'Callaghan, as well as the head of global R&D at her firm, focusing on innovative glass design and technology. There's some really interesting moments of crossover with this group, which I find fascinating. Neil and Andy have worked previously together at WeWork. Neil, Scott, and I all happen to have gone to the University of Michigan, and I'm sure this is just the beginning of many other collaborations, at least I hope so, moving into the future. On this topic, we certainly know that COVID and the pandemic have led to the illustration and evidence around lots of issues around the supply chain. We thought we would zoom out momentarily for this panel discussion and start to think about how the supply chain is in fact a complex system and how we might identify the moments of leverage or the points of leverage in that complex system to be able to have a think about what our opportunities and challenges are today and moving forward. The list of 9 to 1 is credit to Donella Meadows and her work on specifically places to intervene in a system. If you're interested in looking it up, it was written in 1997, so it's almost 25 years old, and I find extremely relevant still today. And the idea is that at the top of the list, numbers, material, stocks, and flows, these are the places that we tend to spend most of our time and our effort on topics in complex systems, but those are the places where it has the least amount of impact. In fact, the most amount of impact is down at the bottom of the list relative to the goals, self-organization, and paradigms or mindsets out of which those goals and systems arise. On the right-hand side of the page, an attempt by yours truly, take it with a grain of salt, to be able to think about the facade supply chain and how that feeds into this framework and how we might be able to start to place some moments and points of leverage around the supply chain moving forward. So with that, and we're just going to leave this up as a backdrop, feel free to reference it if you're interested. And thanks again for joining us for this conversation. Building off of what we've talked about to date, the kickoff question that I wanted to start with is really focusing on the idea of efficiency. We spend a lot of time in the design world and product manufacturing, et cetera, talking about efficiency as a key goal and concept. That's definitely the same in facade design. So my question for the panelists is, how does efficiency inform the tension between customization, optimization, and standardization And how does that ultimately impact the critical outcomes that we've discussed around questions like cost, sustainability, and equity, sort of getting at the idea of the goals of the system? So it's a big question, and if there are no volunteers, I'll name someone, but feel free to jump in.
Is this on?
Yep.
Yeah, I can start. So, I mean, to me, what I love this list. It came, first of all, we had fantastic discussions as this group leading up to this thing. It was a real treat to meet with this team a couple times and talk about supply chain in construction, which I find really interesting as a topic unto itself. So the company that I'm working with right now, we're developers, and this is kind of a new role for me. I come from facade consulting and then into architecture and now into supply chain and development. And looking at the supply chain as a system that can scale, right? So I'm really interested in the big questions that are being posed at this conference today around sustainability. One thing that we're not talking about at all is the housing crisis and the role that we in the supply chain and as designers and architects and engineers and developers play in addressing these big questions and what scale means to that. So to me, the most interesting kind of facet of supply chain is how do we scale? How do we scale solutions, relationships? How do we form partnerships in, between owners and engineers and suppliers to think about scale, to have much bigger ambitions, right? It's not about making the next jewel. It's really about solving really big, I think, important aspects of society that we're faced with today around housing and around sustainability. So I think supply chain is an interesting place to start talking about that because it can't be done alone. It's very much a collaborative. It's about the ecosystem. It's about creating alignments within the supply chain, so pairing up, an informal group of people that are aimed at a particular objective that is not only about solving a problem, but it's about creating healthy businesses along the way, right? Like we're not trying to, I'm trying to help Andy make money and he's trying to help me make money, right? In the process, and at the same time, we're trying to create a product that people want, and we're also trying to do it in a responsible way, right? And taking all of the different kinds of value that we can generate out of that process to the market. So I like the list. I guess to me, the main reason I like it is because it helps me be more ambitious in a way. Like it's about not always operating at the level of just solving the building problem, but having much bigger questions about how do we reorient ourselves towards bigger problems in the environment.
Yeah, I think as a employee of a manufacturing company, we're used to doing all these things on this list inside of our four walls.
Mm-hmm.
We go after problems, waste in manufacturing, right? Lean engineering, all that kind of stuff. But it's interesting to take a step back and say, how do we fit into the larger supply chain, and how can we help? And that's definitely something that's an interesting problem, right? Typically, it's solved with communication,
Mm-hmm.
right? Being more upfront about inventory levels and things like that. I think it's a very interesting problem to solve.
What do we optimize for, I think, is one of the questions, right? So we do a lot of optimization, be it for performance or for cost or for appearance, but where in the point, or where in that process actually, do we come to a solution, and is the solution a product, as you guys are alluding to, or is the solution really where we are right now? Not that at all, but we're just designing from scratch every time a very simple thing, a facade. And how do you get from that point to perhaps designing a product that can be used and applied with components multiple times and really then spend the time on the interesting bits and solve the interesting bits? I think that is where this whole process and problem is very interesting.
Lisa, can you say a little bit more about the project that you're working on that topic?
So we've been for quite a few years now developing a process, not so much a project, but a tool that allows to design facade components that are pre-tested, pre-designed, and that can just be reused, not only in their design, but also or in the process that they are being designed at, but also in the way that profiles can be reused and potentially disassembled afterwards and reapplied to something else. That basically focuses on office buildings and wants to clad about, say, 80% of a building with that system to then allow a design team to spend their efforts and their energy on the 20% that actually really need human brains and human intelligence, and take the rest of it, the standard systems that are very repetitive, and have those pre-solved and just use components that can be kind of mixed and matched, really like a kit of parts or a Lego type of system, and applied to various areas of the building, optimized to the performance requirements and optimized to a certain extent, very importantly, obviously, to cost, but really taking out this endless loop of, resizing a mullion whenever the span changes.
Fair. So what I'm hearing, to reiterate the sort of core concept of efficiency that I'm interested in is Lisa, you're speaking more to the question of efficiency and the benefit being related to human creativity and the opportunity to innovate where it really matters. So there's a human connection there and a human goal in terms of the value that we bring to a process. And Neil, I'm hearing you talk more about the value of efficiency and the goal being more related to social equity, the housing crisis, and the idea that a more cost-effective, efficient system means that we could more rapidly deploy the types of solutions that perhaps Lisa's thinking about. So I'm wondering if you see, is there something in there where those two goals are opposite, or do we think that they're working toward the same process?
Yeah, I mean, I'll weigh in because I think it's, when you think about these sort of systems, the part that is interesting to me is how do you create a system that allows you to create a certain level of efficiency, whether it's efficiency, modularity, streamlining certain things, but being able to create some kind of differentiation so that the product at the end doesn't necessarily mean it's a system that is overly organized. I think some of the things that you see now, especially on the fabrication side, on the technology side, the parts that we're very curious are about where can you actually create inefficiencies to be able to create differentiation, but within a system that sort of plays in a very kind of optimized and tuned kind of way. Because, looking at number 2, every building, every program, every site is quite different. Mm-hmm. So to be able to kind of work within a system that's highly, highly efficient, that allows you to streamline certain parts of it, but at the same time be able to sort of pick spots where you can create the diversification and, again, the inefficiency of certain parts of the buildings because it calls for it is, I think, a sweet spot that I would argue that within this post-COVID world, it forces you to kind of think that way, right? Because we're now thinking about things in a much more efficient way because we're forced to think that way, and it sort of makes you work 3 times as hard to find blips in the system that allows you to create these sort of unique parts of buildings because every building is quite different.
Right. And is that process, from your point of view, because that's what you find interesting, or do you think there's a different goal?
I think it's a need, just like any need for any building. So, as architects, we're dealing with multiple parameters. I'd say that no building is about one singular thing. It's about city, program, cost, engineering systems. So, you know, it's interesting because I see sort of 1 to 9 there, not as a singular choice, but it's a dashboard of dynamic things, you know, as sort of one pulls up this way, another one gets affected, and what have you. So some projects gives you more opportunities on one number versus the other one, just because that's the character of the building. But again, I think it's understanding the current system, understanding where the opportunities are to be able to create certain kinds of diversity that leaves the end product flexible in a very particular kind of way.
Yeah.
And it's hard for, I think, any one of us to be able to kind of dictate that. I mean, it's, you know, these days sort of collaboration is a key word for everything, but I don't know what these guys know. So the more we can sort of understand where those points are is really the only way that you can discover those kind of unique points where you can create anomaly to the system. So that at the end, every building has a particular function, right? In many different ways.
We're talking a lot about systems, which gets pretty abstract in a way. So maybe like bringing it back down a little bit into reality. I think applying systems thinking to what we do is a little bit new, but then at the same time, I think Walter Gropius was trying to create a system, and I think the Bauhaus was trying to create systems. I think that creating systems for the construction of buildings and cities is not a new idea, and I think there's a big ethical component, actually, to this too, and like what kinds of systems are important to cities, and how can we as construction industry professionals scale our solutions to address real problems without imposing kind of a modernist mentality on this, you know, because it's not a new idea to be tackling these problems with systems. I do find that there's a lot of startups now making modular systems, right? Volumetric housing systems in making a proposition about scaling up to address, you know, major construction issues through these systems. And I'm afraid a little bit that that's going to go the way of the Bauhaus or the kind of, you know, the thinking around modernism, and it doesn't reflect the diversity of cities. It doesn't reflect the diversity of places. It doesn't get into the uniqueness of environments. It doesn't. It's a little bit like what happened to industrialized food production in a way, which has kind of decimated our environment. Through the industrialization of food production, we've done a lot of harm to the planet. So I think systems thinking in construction needs to be sensitive to the local environment. I think people that are working on solutions for modular construction and trying to kind of propagate the world with modular construction, I think there's a danger of it being like an overly simple solution in a way that doesn't take place and complexity into account of local city conditions. So to me, it's a fascinating topic of systems thinking. I read about it. I'm no expert in systems thinking whatsoever, but I like applying this to how we think about scale, how we address some of these problems that we're dealing with.
I agree. I think where this framework specifically becomes really interesting for me is down at the bottom, right? Numbers 1, 2, and 3, where we really start to question the way in which the system is thinking, i.e. predominantly what are the goals of the system. So we talk a lot about growth. There's a ton of new construction. There's a lot of population growth. Everybody wants to make a profit. These are really clear goals, and the industry thrives and functions on these goals. What I'm hearing from you is, Lisa, human creativity is a goal. We want to be able to spend our time where we actually feel like we're providing value. Neil, human dignity is a goal, right? People deserve to have good housing. We need to house people and give them a good life. Scott, the notion of human creativity again, and but from a point of view of human experience, and the idea that you know, the beauty and the differentiation within an environment ultimately contributes to our well-being, psychologically, physically, etc. So those goals are fundamentally different from businesses wanting to make profit and grow. how do we use that to think about how to change the current supply chain without it just sounding like a moral imperative? Like we all just want to hug each other, which I like hugging people, but how do we take that feeling, right, and the goals that we all agree are actually really important, and shift that back into the reality of the supply chain? Do we think that anything that's happened over the past year and a half gives us an opportunity to do that?
I think it's even more difficult in the built environment because it is not a product. Buildings are not a product that is being sold to people and only the people that want it, right? But everyone has to experience the built environment whether they want to or not, which kind of puts even more pressure theoretically on us as professionals to really get it right and make for a good experience.
Scott, any additional thoughts on the experience question?
Yeah, it's a big range. I'm not sure. There's a complexity about making buildings that are connected to every aspect of a city that's connected to the supply chain issue. And I think in terms of finding ways to address the supply chain issue, I don't know how you can sort of solve it within the level of a building, because as maybe you were talking about, we're now trying to scale up to find efficiencies within, like at a city level, right? Which is some of the things that I think you may be working on. Because at that level, then you can kind of create, you can find efficiencies, but you can also affect experience within that macro sort of scale.
Right.
So I'm kind of trying to connect the ideas here, and I'm having like a very hard time doing it.
That's fair. Neil, you said you wanted to bring it down earlier. Let's bring it back down to earth. And Neil, if I could put you and Andy on the spot, actually.
Yeah.
I
Perfect.
think that to build off of Scott's point, completely agreed, one building at a time is not going to get us somewhere very quickly. So you both work in product delivery, supply chain. What are the opportunities and the obstacles in that space to affecting real change in relationship to what has happened over the past year and a half?
I'm going to leave in relation to the past year and a half out.
That's fair.
And try to not, so, I mean, I guess just to be really basic, like I think there's opportunities to find strategic alliances in supply chains. It's the most exciting piece. All of the different innovation. I've been sitting in on all these talks today about, different technologies within the glass and glazing industry and seeing all of the amazing research that's going on. But these innovations don't do well on their own. You know what I mean? What we're trying to add up to is an impact in aggregate, right? So I just think that conferences like this are really important. But like within a supply chain, supply chains are kind of the function of an owner, right? You're putting together a team to deliver a project. So I think rethinking how we do that is great. We were lamenting the fact that there's no GC on this panel. I wish there was, because it's the missing link here in a way. The risk and complexity that's taken on by a general contractor in the delivery of a project, sitting between the owner and all of the vendors, is a layer that we're missing in this discussion. How do we create more collaboration across the ecosystem across the supply chain of construction, while respecting all of the liability issues that go into everybody's work, right? Facade being a prime example, right? Where we're working on a condo project. I know when I've had my own practice, like whenever I'm working on a condo project, my insurance goes up a lot. And it's just because it's a point of failure, and it's a high risk item to be working on. And that means that the cross collaboration is actually kind of stifled in a way, because, you can speak to this, I think, a little bit, as somebody responsible for the performance of a facade system. that's very specific, and your liability is sort of describing the boundaries of how much you can collaborate with the rest of the team. So, how do we get around that? How do we work forward? How do we move forward together in R&D to develop better products, better processes, reduce cost, increase efficiency, while contending with the structure of project delivery? I think those are the things that are fighting against each other in my mind for real innovation to happen.
Yeah, I will jump into the last year and a half.
Yeah.
With that, I don't think there's anything. I think what the last year and a half taught us was it was a stress test for the existing state of the supply chain. I don't think it's anything new. I think when you weren't communicating with your vendors upstream, when you weren't communicating with your customers downstream, you didn't have the inventory to cover, hiccups, let's say. I think all those things were exposed, so as things get upset, things get exposed. And I think the real solution to some of the things that you're talking about is that coordination up and downstream, You work together with the roofing contractor as the window contractor to make sure that there's no leaks, and it can be you can sit back and be very confrontational, or you can be proactive and solve the problem. And I know we tend to do better, make more money, have a more successful job when we are proactive. We do the same thing up the supply chain with our vendors, aluminum, glass, all that stuff, right? You get in and you work with them. If you're going to cold bend glass, you make sure your glass guy is okay with it, right? And you all agree on the parameters, and those are the kind of things that I think when you're addressing them up ahead and you're communicating, that's when you can succeed. So, yeah.
I won't talk about the year and a half because you can't escape. But I think one of the interesting things that I've seen is the experience of the whole kind of COVID condition separated these two worlds of sort of front-end work when it comes to facade fabrication and the back end, which is the fabrication. On the front end, my experience is that it sort of proved the incredible resiliency of certain kinds of things that we do in order to do the engineering, in order to do the design. And I'd say it's actually been a stress test to the sort of ultimate degree, and it's sort of been successful because a lot of projects for us, I think, the world sort of stopped, but we were able to continue to have the ability to keep working, at least at the front end of the process. Maybe if the whole world shut down even, let's say, 5 years ago, I think it would have been a very different story, because I don't think we would have the tools developed to the state of things where we were now. I think it would have been a much different story.
Right.
So I think in some ways, it sort of it created a higher level of resiliency through this experience of the year and a half. Now, the back end, which is the fabrication, is quite the opposite. We've had projects where there's lots of difficulties because of all the problems that we know about on the supply chain. So it sort of stress tested that, and there's a lot of scramble to go about it. But it was interesting for me to see the differentiation of the two things, because I'd actually have thought it would be sort of the opposite, that the communication end sort of breaks down the engineering side, and the sort of the fabrication side would continue. But surprisingly to me, it was the exact reverse of that.
Super. We've only got about 2 minutes left, so I think the last question that I'd like to ask is either within this framework or within some other way of thinking that you've been using in your work. At what level? Where are the leverage points in your work today to improve the supply chain, and where do you hope it can go in the future?
The leverage points, I guess, do we pick a number?
Oh, if you want to, sure. Scott's answer is all of the above.
Yeah, all of them, yeah. So, I'm kind of intrigued with I don't know if I have the numbers right, the positive feedback loops. And so I was thinking about that one earlier, and even though it's not super high on the list, how do we create positive feedback loops within the team? So for example, are there agreements that we can sign between parties that create shared alignment or shared goals, right? Mm-hmm. So let's say, I want to grow my business, you want to grow your business, we're looking at this market, We think developing this technology together, we'll both invest in R&D and we'll move forward together as kind of a consortium in building those kinds of ecosystems to address big problems, knowing that single companies can't solve these problems, right? So I think that way to kind of create positive feedback loops where we can generate more value as a coalition of companies. So to me, that for what I'm thinking about now, that's the biggest one.
Lisa?
So I think building on that, for me, it would be a combination of point 4 and point 3. So going back to the resilience that we've seen in our work through the pandemic, and kind of everyone had to learn to self-organize, how do we from that kind of go back and define rules to make sure that we can actually self-organize. So the problem with the self-organization is that at some point everyone has their own rules, and we find that that actually doesn't work. It doesn't bring us any further, and we really need to combine the two and have seen that we're defining a whole new set of rules, whether that is for employment or whether that is for the times that we work, the people that we work with, and perhaps even the supply chain that or the path of supply chain that we go through, and equally perhaps the steps a project takes to get from design to finish. So I think it's, for me, really about a combination of those two.
Andy?
I talked a lot about information flow and knowledge sharing, and that seems like the easy one, but I kind of wish we could work a little more on 1, 2, 3, and 4.
Short and sweet. Scott?
I think it's 2. I think it's 2 because there's kind of a reassessment and re-question of it basically about everything that we do. In terms of the types of work that we do, what we do every day, the types of spaces that we want to be, the types of cities that we want to be. So I think it's a completely different set of parameters that we're now talking about with completely different goals in terms of what we want to achieve. So, 2.
I hope that's true.
I hope so too.
I hope that's where we're headed. So thanks again for joining us. I wanted to reiterate that, the past year and a half or not, but particularly within the frame of reference of COVID, of George Floyd, of climate action, Greta, et cetera, we are in a really, really interesting moment where there is actually a lot of opportunity and activity in the question around goals and mindset and paradigm change, and I think we have a great opportunity to really question that within our work, within the supply chain, and all the projects that we're working on. So thanks again.
Now, did you take the photo? Yeah, thank you. Because I'm being asked to be in the second one, but take them first. as soon as someone moved in the chair. Yeah.
Yeah, I was trying to not move so that it doesn't. Yeah.
It's Scott, right? Yeah. So you should have stood up in the back.